The fundamental theorem of calculus, discovered by Newton and Leibniz back in the 1600s, is one of the most amazing and useful facts in all of mathematics. In most calculus textbooks, the fundamental theorem of calculus, or FTC for short, is typically broken into two pieces, called the First Fundamental Theorem of Calculus and the Second Fundamental Theorem of Calculus. The goal of this video is to do something kind of strange. We're going to prove the First Fundamental Theorem of Calculus using the Second Fundamental Theorem of Calculus. Be sure to stick with me until the end of this video, and I'll share with you all the math resources that I have here at my YouTube channel, Bill Kinney Math. So let's start by looking at the statement of the First Fundamental Theorem of Calculus. Suppose that little f is a continuous and real-valued function over the entire closed interval from a to b, where we assume here that a is less than b. Also suppose that capital F is an antiderivative of little f on the entire interval. In other words, capital F prime of x equals little f of x for all x in the entire interval from a to b. Then the conclusion is that the definite integral of little f of x from a to b can be found by computing capital F of b minus capital F of a. This is really amazing and mysterious. We can find areas under all sorts of curves, which is what the definite integral represents, and which have applications to a lot of areas, including, for example, statistics, if we can only find antiderivatives, plug numbers in, and do subtractions. Of course, if you have any experience with this, you know that antiderivatives are sometimes very hard or impossible to find. In such a situation, we would have to resort to numerical integration to approximate the integral. It's not that the fundamental theorem of calculus is false in such a situation, it's just that it's not helpful. But it's still a beautiful fact that is very useful that we want to understand and prove. Why is it called the First Fundamental Theorem of Calculus? Probably because it's the one that people use the most and are therefore the most familiar with. However, we're really going to see that the Second Fundamental Theorem of Calculus is broader because we're going to use it to prove the First Fundamental Theorem of Calculus. Maybe these names, first and second, really should be switched around. Before looking at the proof of the First Fundamental Theorem of Calculus, let's look at its use in a basic example. Let's compute the integral of x squared from 1 to 2. How? Well, compute an antiderivative. Capital F of x equals 1/3 x cubed, you should know from derivative facts, has the property that capital F prime of x equals little f of x equals x squared for all x. Therefore, we can say that this definite integral of x squared from 1 to 2 equals capital F of 2 minus capital F of 1. When you plug those numbers in, you get 8/3 minus 1/3, which is 7/3. Here's the graphical interpretation. The red graph is the graph of x squared. The blue shaded region is the area that we are after, the area under the curve, which is the integral from 1 to 2, and that area equals 7/3. Take a few seconds to look at this and see that it seems reasonable that the area should be close to 2.3 repeating. But why does this work? And is it just too good to be true? Why is it true? We want to understand, at least based on the Second Fundamental Theorem of Calculus. Before looking at the proof, it's a good idea to think carefully about what needs to be done to actually do the proof. The First Fundamental Theorem of Calculus is a theorem. It's a mathematical statement that must be proved using deductive logic, to start with the premises of the theorem, the assumptions, and show that the conclusion follows. So, for the First Fundamental Theorem of Calculus, which I will shorten to First FTC, we would need to assume the premises, that we are given a continuous function little f of x defined on the entire closed interval, and in fact continuous on that entire closed interval, and assume we have another function capital F of x such that capital F prime of x equals little f of x for all x in the interval from a to b. We would then need to verify the conclusion, the equality that the definite integral of little f of x from a to b equals capital F of b minus capital F of a. Doesn't seem very clear what to do, does it, when you think about it? One approach would be to use the definition of the definite integral as a limit of appropriate Riemann sums. Maybe you've heard about Riemann sums before. I hope you have. This can be done, but it's not very easy. There are a lot of subtleties to prove something like this in its full generality. Riemann sums are difficult to deal with, especially when you think about them in the most general way. This approach also requires using something called the mean value theorem, which you might want to look up. A second approach, which is our entire goal for this video, is to use the Second Fundamental Theorem of Calculus, the second FTC. Though again, this might seem like putting the cart before the horse. We're using the second FTC to prove the first FTC, And again, maybe we really should switch the names around, and in fact some people do. But what does the second FTC say? Here's the statement. Suppose that little f is a continuous real-valued function on the entire closed interval from a to b. That's the same as before. Suppose now that I define a new function, capital A, with this formula. Capital A of x is the definite integral of little f of u du as u ranges from a to x. Now this is a confusing definition for many people when they encounter it. You need to realize that for any given value of x in the entire interval from a to b, this definite integral will exist because little f is continuous, and we are going to get a value, capital A of x, that will be different for different values of x. This does define a function of x. Why am I using the letter u in the integrand? Well, I needed to use something, and I did not want to use x. I wanted to keep x separate as the upper limit of the integral. I could have used v, I could have used w. There's lots of letters that I could have used. Anything but x. What is the conclusion? Then a is differentiable, has a derivative on the entire interval from a to b. Moreover, the derivative capital A prime of x equals little f of x for all x in the interval. In other words, capital A is an antiderivative of little f. Proving this theorem, however, requires knowledge of Riemann sums. So what have we gained? Well, what we've gained is we're going to just use the theorem to do the proof of the first FTC, and we're not going to worry about Riemann sums. Now that might seem like cheating. However, there is a benefit to doing it this way, besides the fact that you have kind of a neat proof of the first FTC. That benefit is that the second FTC, when you understand it well, at least, is actually a bit more intuitive than the first FTC. The first FTC kind of seems like magic. To do the integral, just compute the antiderivative and compute the difference. The second FTC can be more intuitive if you think about areas. Geometrically, the second FTC says that the rate of change, the derivative, of the accumulated area function capital A of x. If the graph of f is above the axis, capital A of x is the area under the graph from little a up to x. That's accumulating areas as x increases. When little f is above the axis, capital A will be an increasing function of x. More and more area under the graph of little f will be accumulated. So again, the rate of change of capital A, the derivative of this, equals the height little f of x. In other words, capital A prime of x equals little f of x for any given value of little x in the interval from little a to little b. Here's a picture. The red graph is the graph of little f. Y equals f of u. I'm labeling the horizontal axis here with u. I'm thinking of u as the independent variable for little f. I'm thinking of little a and little x in this picture as being fixed. And the blue shaded area, labeled capital A of x, is the area under little f. It's the integral of little f from little a to little x. The derivative, capital A prime of x, equals the value of little f of x. It's the height of the right side of the shaded region. As that gets bigger, a prime gets bigger, that means area under f is being accumulated faster and faster. Now we are finally to the proof of the first FTC using the second FTC. So we need to start our argument by assuming the premises of the first FTC. Assume that little f of x is a continuous function on the entire closed interval from a to b, and assume capital F of x has the property that capital F prime of x equals little f of x for all x in the interval. Capital F is an antiderivative of little f over the entire interval. By the second FTC, we're going to use it right away. Define a new function capital A of x to be the integral of little f of u du as u goes from a to x, and do this for all x in the entire interval from a to b. Then, because of the second FTC, we can say that capital A prime of x equals little f of x for all x in the interval, just as was true for capital F. In other words, both capital F and capital A are antiderivatives of little f. Capital F is by assumption, capital A is by the second FTC. Also note that capital A of little a is the integral of little f from a to a, which has to be zeroed by properties of integrals. There's no area under the graph of f above 1 point. In other words, like I just mentioned, the derivatives of capital F and capital A are the same for all x in the interval. But this means that the slopes of the graphs of capital A and capital F are the same at every value of x in the interval. They must be vertical translations of each other. There must be some constant, call it capital C, so that capital A of x equals capital F of x plus C for all x in the entire interval. Though I should say, even though this is an intuitive fact, technically speaking, this fact requires the mean value theorem for its proof. So in reality, we can't get away from Riemann sums. We also can't get away from the mean value theorem to prove the first FTC. Now, by definition of the function capital A, I can say that the definite integral of little f from a to b, and don't be bothered by the fact that I'm using an x here instead of a u, I could have used a u, equals capital A of b minus 0 because of the definition of capital A, and because 0 doesn't affect the value. But remember, on the previous slide, I said that capital A of little a equals 0, so I can replace that 0 with capital A of little a. But then I can use the relationship in the first bullet point above to say that capital A of b is capital F of b plus c, and capital A of little a is capital F of a plus c. And then when I subtract those two things, the c's cancel, giving me capital F of b minus capital F of a. That's what I wanted. We are done. That's the final conclusion. Q.E.D, quod erat demonstrandum, is a common thing to say at the end of proofs. I, being a believer in God, also say PTL for praise the Lord. All right, now we're at the end. I'd like to thank you for watching to the end here, and please ask you to subscribe to my YouTube channel, Bill Kinney Math. I'd also suggest checking out my blog. It's called infinityisreallybig.com, and follow me on Twitter. There will be some more content like this to come in coming months. I also have almost 1,000 lectures, problem-solving videos, Mathematica videos, which is a computer program, and more on YouTube already that you can find by just searching Bill Kinney and then whatever subject you're interested in. The lectures cover many classes, many courses, though I will say my most popular lectures are on real analysis, abstract algebra, financial math, and complex analysis. Right now, here in fall of 2020, trying to deal with COVID, I'm also making lectures on differential equations and linear algebra. My blog on mathematics, applications, life, and Christian faith is infinityisreallybig.com. I've got a lot of interesting stuff on there, I think, that you'll find helpful. Finally, you could follow me on Twitter. I don't have a ton of followers here at the moment, but hopefully this video will help me gain a lot of followers. I will be doing a lot of tweets about math in coming months. Thanks for watching.